Chapter 3: Mathematics of the Cube. Geometrical, mathematical, binary, logical, algorithmic, and physical fundamentals of the cube. Binary and arithmetic model. The math of a cube begins with the number 0. 0 times 0 equals 0. 0 plus 0 equals 0. 0 divided by 0, 0 minus 0, or any number multiplied by 0, they all yield 0. On the other hand, we have the number 1. 1 times 1 equals 1. 1 divided by 1 is 1. 1 square yields 1. The square root of 1 is 1, and any number multiplied by 1 yields that same number. These numbers are important because they represent divinity. They are indivisible and impose their essence into the others. We place the number 0 and 1 on opposite sides of a straight line. We will call this line the x-axis. Cartesian coordinates. When a line is intersected by an identical line from 0 to 1, y, to create a bidimensional Cartesian coordinate system and obtain 4 combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Cartesian map. Based upon a square, René Descartes proposed a model from which a whole rational train of thought was developed. Using the lines as axes, René Descartes created a method to map mathematical functions. This coupled with his Cartesian method, which is the basis of the scientific method, and therefore the Occidental civilization. In the Cartesian plane, 2 axes are intersected from the middle to create 4 equal spaces, where one can trace roots, and these roots are the result of formulas. As an example, let's study the formula y equals x2. Since we have 2 axes, the first dimension being x and the second dimension being y, then we can draw the trajectory of x2 as follows. The function x to the second power equals y. The function x to the second power has a minimum value of 0, and after that, whether x is a positive number, 1, 2, 3, or negative number, -1, -2, -3, the result grows exponentially, as illustrated in the following chart. This is what a plane illustrates and what René Descartes discovered, that how to draw maps using the square or Cartesian plane. Arithmetic of the Cartesian coordinates. In the Cartesian plane, each of the binary combinations has an arithmetic value. This is obtained by multiplying each binary combination with a value or weight of the variable. Not all variables are equal in every model. Some are more valuable than others. In this model, x is the body and y the mind. We give the mind a higher value 2 than the body 1, since body is what we have in common with all plants and animals, but mind is what differentiates us from them. The cube. We then intersect an identical line or axis z, also going from 0 to 1, to create the tridimensional cube and its 8 combinations. Arithmetic of uCube. As in the Cartesian coordinates, each of the binary combinations has an arithmetic value. Again, we set a higher value or weight to the z-axis for spirit, which is a higher weight than the mind or body. Spirit is what differentiates each human from another, and the motive spirit has a higher value than game mind or the rules body. Geometry of uCube. The only geometric figure that fully resembles the complexity of reality is the sphere. However, it has an infinite number of variables, and therefore it's not useful for modeling. The mission of every model is to simplify our understanding of reality, and a sphere hardly accomplishes such mission. It's too perfect for modeling reality. We chose the cube, knowing its limitations, vis-a-vis the sphere, but we should be well aware that the cube is a tridimensional figure that fits into our tridimensional world and still has some perfection of its own. First dimension. The geometry of the cube also begins with the number 0. However, in geometry, we call it emptiness or space. Emptiness has no dimensions, and it does not exist on this planet. No one has ever seen emptiness. It's just a product of our imagination. It's the same with the dot, which also has no dimensions. Even a dot painted in a blackboard or monitor can be a complex structure of tridimensional fractals or lights, so both empty and dot exist only in our imaginations. If we connect 2 dots, then we get a line, and that is considered the first dimension. Again, no one has ever seen a line or the first dimension. The plane or second dimension. If we add another dot and unite both extreme ends of the line to the dot, we get the simplest plane, which is the triangle. However, Triangles are not good modeling tools because the three variables are codependent and any movement in one point alters either lines or axis, A to B. In order to model, we need a plane that allows for a dependent and independent variable, and that plane is the square, which is obtained from uniting the extreme ends of two identical lines. Planes do not exist in this world either, just like with space, dot and line. They are mental abstractions. No one has ever seen or manipulated a plane. The perfection of the square. The square root of 2, also known as Pythagoras constant, is the positive real number that, when multiplied by itself, gives the number 2. Geometrically, the square root of 2 is the length of a diagonal across a square with sides of 1 unit of length. This follows from the Pythagorean theorem. It was probably the first number known to be irrational. Its numerical value truncated to 65 decimal places. This is an irrational number, which means that its value cannot be expressed exactly. A NASA computer has calculated 10 million decimal digits without finding the exact number. In this irrational number lies the perfection of the square, the prism or third dimension. If we add a dot to a plane and we unite the extremes, we build a plane. The first tridimensional object and the simplest prism, it is a pyramid. However, we cannot model using the pyramid because the movement of one point, A to B, causes all the others to move as they are all independent. The first prism that allows tridimensional modeling is the cube, which we obtain from uniting the four extremes of two squares. Prisms do exist in the world. Actually, the world is built on prisms, so we need a prism to model our tridimensional world. The perfection of the cube. The square root of 3 is the positive real number that, when multiplied by itself, gives the number 3. It is also known as Theodorus constant, which was named after Theodorus of Cyrene. Geometrically, the square root of 3 is the length of a diagonal across a cube, with sides of 1 unit of length. This also follows from the Pythagorean theorem. Its numerical value truncated to 65 decimal places. This is also an irrational number, which means that its value cannot be expressed exactly. A NASA computer has calculated 10 million decimal digits without finding the exact number. In this irrational number lies the perfection of the cube. The perfection of the sphere. Pi, sometimes written pi, is a mathematical constant whose value is the ratio of any circle's circumference to its diameter in Euclidean space. Geometrically, this is the same value as the ratio of a circle's area to the square of its radius. Its numerical value truncated to 65 decimal places is. It is an irrational number, which means that its value cannot be expressed exactly. A NASA computer has calculated 10 million decimal digits without finding the exact number for pi. In this irrational number lies the perfection of the sphere. Why a cube? In reality, the cube has floor, walls, and roof, height, length, and depth. In a cube, we can move up or down, left or right, and front and back. This is not the case of the sphere, that has no roof, floor, or walls. In a sphere, we can move up or down, left and right, and back and forth, but no matter in which direction we move, there is an infinite number of points surrounding us. In a cube, we get closer and further from 8 well-defined ends. Finally, the cube is tridimensional, so we don't need more to model our reality. The cube is merely for illustration purposes to help anyone understand this model. But in reality, as long as there is a tridimensional space, the model works as long as there are 3 axes, x, y, and z. Calculus model. Reality is one big tridimensional fractal, and using cubes we can replicate that fractal reality. uCube can be derived into inferior or microcubes, or integrated into superior or macrocubes. Every cube is both macro and micro. It's part of a superior cube and made of inferior ones. Just like in a family, a father is also a son and a mother is also a daughter. Calculus model. To integrate cubes, one must convert the chaos and order of 3 microcubes into the extremes of the 3 axes of a macrocube. To derive microcubes from a macro, one must do the opposite. Each cube has order and chaos. When integrating order and chaos of micro becomes the extremes 1 and 0 of an axis of macro. How do the model works? Let us illustrate how to derive or integrate cubes. For that, we will use the first cube introduced, Marx Fukuyama, which has economic, political, and social fractals of chaos and order. The political axis X has tyranny on one side and democracy on the other. The economic axis Y has depression on one side and development on the other. The social axis Z has discomfort on one side and well-being on the other. The six extremes, tyranny, democracy, depression, development, discomfort, well-being, are the chaos and order of their respective political, economic, and social cubes. Society equals F, economy, politics, social. Economic, political, and social microcubes. The macro society cube is built out of three microcubes, one for politics, one for economics, and a social cube. Tyranny or political chaos, 000, happens when there is no rule of law, no consensus, institutions, or no participation or accountability. Democracy or political order is the contrary, the rule of law, which consensus, institutions, participation, and accountability. Economic chaos or depression is defined as instability, wealth, destruction, and wealth concentration. Economic order or market is the resulting interaction of stability, growth, and distribution. Social chaos or discomfort is a society without health, work, or culture. Well-being is the contrary, a healthy, occupied, lively, and educated society. Chaos and order are the result of the interaction of the political, economic, and social essences in each cube as illustrated next. Methodological note: chaos and order of each microcube become an axis in the macro cube. The political cube becomes the political axis of the macro cube. The economic cube becomes the economic axis, and so does the social. And then each of these microcubes are also built of smaller ones, and so on, as deep and profound as one's wishes. The cube is truly a modeling tool because it's capable of reaching high degrees of complexity. Yet it's a simple, logical, and easy-use tool that even a child can understand and manipulate. It also gives the modeler the freedom to choose variables at will. Not all may agree that the three variables of the economic cube are growth, stability, and distribution. They have the freedom to consider alternatives as long as they stick to the methodology to have rules, game, and motive, a material, intellectual, and spiritual essence. A note about the U.S. It used to be the greatest country on earth, the land of opportunity and home of the brave, but politically, there are less and less consensus and institutions have been significantly weakened. Unable to reach broad agreements, the latest presidents have restored in many instances to executive orders, and the rule of law is being questioned by the arbitrary application of new laws that favor the government hurting the individuals. Economically, few countries in the world concentrate wealth as fast and to the extremes that the United States is doing. Never in the history of the nation has so much wealth and power been concentrated in so few hands. Debts and deficits are at nightmare proportions, and the dollar has lost 90% of the purchasing power it had only 50 years ago. Socially, there are now at least 40 countries with higher degrees of economic freedom, longevity, education, employment, and quality of life than the U.S., who leaded the world in all these metrics for many decades. Bringing the model down to earth. We can now feed numbers into the model. On the political cube, we can use voter turnout to measure participation. We can use corruption indexes to measure rule of law and consumer confidence to estimate consensus. We can now calculate a point inside the political cube and chart a point with a political index. On the economic cube, we can feed inflation to measure stability, growth to measure wealth creation, and the Gini index for distribution. Illustrate with a point where the economy is in the cube. For the human rights cube, we can feed health, education, and occupational indexes to measure the well-being of a society. The 3 points in each microcube combine with the macrocube for the society index. And so, the cube can be used to model reality and build complex relationships between variables. in order to understand the world around us. With this understanding of reality and the ability to go deeper and deeper, uCube can be the basis of a very successful consulting practice. Physics of the cube. The cube also complies with the rules of physics, including energy, mass, and volume. The energy of the cube increases as we approach order 111 and decreases the closer we get to the chaos. Also, since the cube is a prism, it can contain volume, as if it was a tub with water. Finally, the cube complies with Newton's laws of motion, inertia, force, and dynamics, which means that in our tri-dimensional world, energy moves on three vectors. Chaos is defined as entropy, whereas order is defined as synergy. Energy cube. Energy gained from chaos to points 100, 010, and 001 will always be 1. From chaos to 011, 101, and 110 will always be 2. And from chaos to order will always be 3. Energy lost from order to 011, 101, and 110 will always be -1. From order to 100, 010, and 001 will always be -2, and from order to chaos, -3. In the balance, approaching order creates synergy, while approaching chaos creates entropy. Newton's laws of movement. The cube proves that Newton's laws of movement are tridimensional also. The rule is that in the absence of a net force, a body either is at rest or moves in a straight line with constant speed, inertia, Newton's first law. The game is that when subject to a force, a body experiences an acceleration equal to the time derivative of a momentum, force, Newton's second law. Finally, whenever a first body exerts a positive force on a second body, the second body exerts a contrary force on the first body equal in magnitude but opposite in direction. Dynamics, Newton's third law. He did not know it, but Isaac Newton, the world's most important physicist to ever exist, was playing with uCube. Newtonian cube. In a tridimensional space, positive and negative forces coexist because, as Newton discovered, all forces come in pairs. For simplicity purposes, we normalize the cube and assign each axis to the range 0 to 1. But in terms of energy, cubes are not neutral. They have a positive and a negative polarity. In other words, for each positive cube, there is a negative exerting energy in the opposite direction. Synergy, the whole greater than the sum of the effects of the individual parts. Tridimension means volume. The volume is how much three-dimensional space it occupies. One-dimensional figures and two-dimensional shapes have zero volume. Hence, they can't exist in a three-dimensional world where everything has volume and occupies space. Matter takes only three forms: solid, liquid, and gas. Having volume is not a minor feature of the model. Instead of a point moving in space, we can view reality as a ball floating in liquid and moving around the cube, depending on the energy supplied or removed from the system by each of the variables. Thermodynamics of the cube. Thermodynamics is the study of energy conversion between heat and mechanical work, and subsequently the macroscopic variables of temperature, volume, and pressure. Systems can gain or lose energy. A buoyant economy arguably increases the energy of the system, whereas the contrary, a depressed economy diminishes the energy. Thermodynamics may explain energy gains and losses within a system, as well as phenomena such as the overshooting in financial markets, or why fear causes markets to react more than greed. Cube algorithms. Algorithm, as defined by Wikipedia, is a list of well-defined instructions for performing a task from a given initial state through well-defined successive states to a desired end state. The cube has well-defined algorithms for solving the complex puzzles that challenge us daily, for ordering our chaos. These algorithms have one thing in common. Sooner or later, they move along the three axes. Momentarily, they may move in one or two, but to go from chaos to order, one must move on all three. Rubik's Cube. To explain algorithms for ordering chaos, we use the first cousin of the uCube, the Rubik's Cube, a tri-dimensional puzzle invented in 1974 by Hungarian sculptor and professor of architecture Erno Rubik. This puzzle, the most successful ever, it has sold 300 million copies since its inception. and has an astonishing 43 quintillion different possible configurations of chaos and only one solution of order. Algorithms of chaos and order. Yes, 43 quintillion, 252 quadrillion, 003 trillion, 274 billion, 489,856,000 permutations, and 519 quintillion, 024 quadrillion, 39 trillion, 293 billion, 878 million, and 272,000, or 519 quintillion possible arrangements of chaos, but only one order. And there are formulas for transiting from any one of these chaos to order. The chaos of trial and error. We will not enter to the detail of the algorithms on how to solve Rubik's Cube, but if these algorithms are known, the puzzle can be solved in 26 moves, in just a few minutes. If not, it can take 26 years, like Graham Parker from England. Algorithm analogies. In order to solve the Rubik's Cube, the first step is to order one of the walls. Then, one has to break that order several times to attend other chaos within the cube, and repeat it many times before the puzzle is solved. Same with uCube. A government that wants to stabilize an economy and then maintain that stability at all costs will end sacrificing distribution, derailing growth, and ultimately losing the precious stability also. One has to move on all axes, like in Rubik. Mexico is a good example of the above. Throughout decades, technocrats and the Washington Consensus forced Mexico into a straitjacket. Initially the shop plan worked, but then income began concentrating, which killed the domestic market, and growth rates dropped to the slowest pace in Latin America. Such is the result of daring to sacrifice some stability to move in the vectors of growth and distribution. In late 1994, a financial crash destroyed economic stability, and the country entered the Great Depression, which endures today. Mexico was among the countries hit harder by the subprime global crisis. In 2009, the GDP per capita fell 10%, throwing 20 million to poverty. Mexico's average growth in the past 30 years is less than 1.2% per annum, with a population growth of almost double.